So, this is the matrix notation. Now, I want to discuss something known as a stationary distribution. Okay. So, I am given a finite state DTMC with transition probability matrix equal to P. Intuitively, a stationary distribution is a distribution among states that does not change with time. Okay. Stationary distribution is a distribution, it's a probability distribution over states, over the state space S, let me call it over S, that does not change with time. Okay. So, what does that mean, right? So, we do not know if such a distribution exists, right. What I mean is that, is there a distribution over the states S? This is a finite state DTMC. So, is there a probability mass function corresponding to the various states in the finite state DTMC? If I start in such that if I start in the distribution, I always remain in the distribution, right. Please note that if I start in a particular distribution at time 0, all right. If it so happens that the distribution at time 1 is the same as the distribution at time 0, then since the Markov chain is homogeneous, the distribution at time 1 to time 2 will also be the same, all right. So, the question is there a stationary distribution that is an invariant or stationary distribution if you start in the distribution such that if you start in the distribution, in the next step you are in the same distribution, right. So, that is the question. Does there exist a distribution over the states? Usually it is denoted by pi, okay. Say pi I is equal to 1 2 dot 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 m such that if probability that x naught equals I is pi I for I is equal to 1 2 dot 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 m, then probability that x n equals I is pi I for all n greater than or equal to 1 and I in all the states there. Now, because of the Markov property, it is enough to ensure if at all it is possible, it is enough to ensure that probability that x 1 is equal to I is equal to pi I, right, for I is equal to 1 2 dot 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 m. Because if you start at time 0 at in the distribution pi among the states and you remain at pi at time equal to 1, then because of Markov property, the homogeneous Markov chain, you are going to remain in pi for 2 and 3 and so on, right. So, it is enough to ensure this, right. Now, let us look at this, right. We want, so we just want to ensure this, right, want probability x 1 equals I equals pi I, right. but what is probability x1 equals I? This can be written as probability that x1 equals x1 equals I given x naught equal to j times probability that x naught equals j. By the law of total probability, this is just sum over j equals 1 to m, right. This is the law of total probability. You want to end up the probability that x1 equals I is simply probability x1 equals I given x naught equal to j times probability x naught equal to j. But of course, you are starting, so this is equals pi j. You want to start at the distribution pi j over states, pi I over the states, and remain in that pi I, right. So, what we want is that, so this is equivalent to saying, what is this equivalent to saying? It is equal to pi I equals sum over j equals 1 to m. This guy is just p j I, right. This is the jith entry of the transition probability matrix. This is pi j p j I, right. So, this I want for I equals 1 to m. So, for each state I want pi I is equal to sum over j equal 1 to m pi j p j I. Of course, we do not know if such a pi even exists, right, and we want also want, so it is a distribution after all, right. So, I want to be able to say that it is normalized over the states, right. The question is, does there exist a distribution pi that satisfies this? If it did, right, I do not know if it does, but suppose I tell you that there is these m probabilities pi i's which of course sum to 1 that satisfy this equation, all right. Then I am guaranteed that if I start in this pi I at time 0, I will remain at this pi I distribution at time 1 and then therefore at time 2 and therefore for all n, right. So, if there exists a solution to this set of equations, right, which I have put it in the box here, then you are guaranteed that if you start in that distribution, you will remain in the distribution forever, okay. This pi is known as a stationary distribution of the DTMC, all right. I have not said anything about whether such a pi exists. All that I am saying is, if it did exist, it should satisfy these equations, correct. So, we will proceed to study when it exists, when the solution exists, when it is unique and all that, right. So, let us just say, so a stationary distribution for an m state DTMC is a distribution over the states that satisfies. So, I can write this equation right here, this equation in the matrix form. That is what I am going to do. If it satisfies, pi is equal to pi p, all right. So, this pi is a row vector of these probabilities pi 1 pi 2 dot 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 pi m, all right. P is of course the transition probability matrix, okay. So, the equation pi I is equal to sum over j pi j p j I can be written in matrix form as pi is equal to pi p, right. And of course, pi is a probability distribution, so it should be normalized. I do not have to explicitly say this because it is a distribution of all the states, but nevertheless I am putting it down explicitly. Okay. So, a normalized vector of numbers which satisfies pi is equal to pi p is known as a stationary distribution of the M state DTMC. Notice that I have said a stationary distribution, right. I have not said the stationary distribution. The reason I deliberately put a instead of the is because it is possible that there are many stationary distributions, right, as we will see, all right. So, this pi is equal to pi p is some sort of a cornerstone, okay. It is a very important equation when studying finite state Markov chains, and also similar thing we will also study for infinite state Markov chains, except that P is not a matrix, it will be an infinite dimensional entity, right. So, these equations are known as the global balance equations. All right, pi is equal to pi p and sum over pi is equal to 1, known as the global balance equations. Okay. Intuitively, what does that mean? So, you are writing, so let me just write this down again, pi I is equal to sum over pi j pji, all right, j equals 1 to m. So, what we are saying is that the probability of being in some state I, right, is the probability of being in some state j in the previous time and then jumping to state I in the next time, all right. So, you will do this over all possible states, right. So, you look at a state I, you are looking at the stationary probability of stationary distribution of the state. So, you are looking at the probability that you are in state I. This balance equation is essentially saying that the probability of being in state I is equal to the probability of being in some other state j in the previous time and then jumping to I, which is with probability pji, right. And of course, you have to go over all the states that you could have been in the previous time, right. So, it sort of globally balances all the probabilities, right. That is why it is called the global balance equation, all right. Pi is equal to pi p in matrix form, or pi I is equal to sum over j pi j pji, all right. So, this is the picture to keep in mind. Okay. Now, so far we have not said anything about the existence of pi or about its uniqueness, right. All we are saying is that if a probability vector pi were to be a stationary distribution, it should satisfy pi is equal to pi p. And conversely, if it satisfied pi is equal to pi p, it would be a stationary distribution in the sense that it would be invariant over time, all right. So, there are several questions that arise. First, does there always exist a solution to pi is equal to pi p, right, existence. The next questions after existence is, suppose if it did exist, is the solution unique, is the solution pi unique, right. You can go further even and ask, suppose I do not start in the stationary distribution pi, suppose I start in whatever distribution I want, or I start deterministically in some state, all right. So, I do not care where I start, I do not have to start in pi, I start in whatever distribution I want and I let this Markov chain run for a very long time, all right. Then after a very long time, if I run this Markov chain for a million time steps, is it true that the Markov chain after a very long time, will the probability of being in state I approach pi I, which is the stationary distribution, right. So, pi is equal to pi p is some sort of a stationary property. Now, I am talking about an attraction property. So, if I start off in whatever distribution I want and let the Markov chain run for a long time, am I assured that I will attract to this pi after a long time, right. These are all important questions that we need to understand about finite state DTMCs. Now, let us discuss long term behavior. Suppose we do not start in the stationary distribution pi, right. So, I am going to let the DTMC run for a long time. Okay. Then is it true that the n step transition probability, let us look at p x n equals j given x naught equal to I, which is our old friend p I j n, and consider it as n tends to infinity where n is large, right. What does it converge to, right? Does it converge at all? I do not know, and what does it converge to, right. So, let us look at what it might converge to, right. So, ideally I would like this p x n equals j given x naught equal to I to forget where I started, right. If at all it converges to something, ideally I would like it to be some function of just j, right. Suppose I look at this equation probability. So, suppose I look at p I j n plus 1, alright. I want to go from I to j in n plus 1 steps. This is of course is equal to sum over k is equal to 1 to m p I k, go from I to k in n steps and then go from k to j, right. This is I am just rewriting the n step transition n plus 1 step transition probability matrix, the ijth entry in terms of the product of the ijth, it is p to the n times p is what I am writing, p to the n plus 1, alright. Now suppose, so as n tends to infinity, what happens to this, alright. By the way, this equation is very important equation. This is known as the Chapman Kolmogrov equation. Actually, you can write it more generally. I can write Chapman Kolmogrov equation is written as p I j m plus n is equal to sum over k p I k m p k j n, alright. So, I have to go from I to k in m steps and k to j in n steps. Okay, this is actually called the Chapman Kolmogrov equations, alright. So, anyway, so I am back to this considering what happens to this equation as n tends to infinity. Okay, so let me put this in a separate box. I am considering this as n tends to infinity. I want p I j n plus 1 to converge to some number which is only a function of j, right. And likewise, I want p I k n to converge to some function of k, right. Say, I mean, I do not know if this happens, but say p I j n converges to some nu j as n tends to infinity, okay, some number nu j, it is between 0 and 1, alright. Then such a nu j, this is for all j in the states. So, this then I would have nu j is equal to sum over nu k p k j, k equals 1 to m, right. Such a nu, if it were to converge to a number nu, then it would have to satisfy this equation, alright. But this equation is already familiar to us, it is simply pi is equal to pi p, where pi is, I am just calling it nu, right. I might as well just call this pi, right. This is our old friend, right. This is, why did I call it nu? I could have just called it, I called it nu because I did not know what it was, right. But looking at this equation, these nu's are just pi's, right. Just pi j, right, just our old friend pi j. What does that mean, right? So, if p I j n were to converge to something, some function of j alone, where the memory of the initial state is lost, then that what it converges to, p I j n converges to is pi j, which satisfies pi is equal to pi p, right. So, I am talking about two things now. So, one is stationary distribution, right, where if you start in the distribution pi, I remain in the distribution pi, and such a pi satisfies pi is equal to pi p, right. So, there you have to ask, does there exist such a pi and does such a pi exist uniquely? Next, I am talking about long term behavior, where I do not have to start in pi. I start in whatever state I want, let us say state I deterministically or whatever distribution I want. Do I converge to something that forgets where I started, right? If Pij were to converge to some function of j, right, some probability, that probability has to be pi j which satisfies pi is equal to pi p, right. So, that is the key issue. Okay. So, we can pose some very important questions. Which we will subsequently answer. Question 1. Under what conditions does pi is equal to pi p have a solution, have a probability vector solution? Question 2. Under what conditions is the solution unique or non-unique? So, these are existence and uniqueness questions for the stationary distribution. The third question is a long term behavior question, which I alluded to just now. Under what conditions does Pijn converge to pi j as n tends to infinity for all j equals 1 to m, right? Or in other words, if you look at the nth power of the matrix, under what conditions, question mark, right, under what conditions does this converge to the vector of all, you know, pi pi pi. What we want is that Pij to go to pi j, right, Pijn to go to pi j. In other words, you want the if you look at the nth power of the matrix P, as n becomes large, you want all the rows to be pi pi pi, right. That is just the matrix version of what I have said here, right. Under what conditions does this happen, right. So, these are the questions we have to understand about stationary distribution and long term behavior of finite state DTMCs, all right, and we will address these questions in the next few modules. I stop here.